Okay, so everybody will come now to the second part of our double header today. So it's Victor Gayral from the Université de Reims Champagne-Ardenne, and he will speak about quantization of locally compact groups from dual true coordinates.
All right. So first of all, I would like to thank you, Raymond, for this kind of surprise invitation. And I mean, it's my real pleasure to be here and to talk about. So this is about a collaboration for a couple of years with Pierre Bielawski, Sergei Nevsheyev, and Lars Tusset. And yeah, so you'll see, but the goal is to construct a concrete example of non-formal Drinfeld twist. I'm going to be more precise. Okay, so the context is the context of locally compact quantum group in the setting of Feynman algebras. I mean, you can also look at it in the setting of C-star algebras. There is no major difficulties. It's rather a question of taste, and I prefer to stay with Feynman. Okay, so quickly, what is a locally compact quantum group in that sense? It's a Feynman algebra, a coproduct, and something which is very important because it's no longer a theorem but an axiom. You need existence a priori of invariant weights, the left and right R weight, and that's what makes a big difference between the compact or compact and discrete world and the locally compact case, because in compact or discrete, you have existence theorem for weights, which is not at all the case in the genuine locally compact case, and it explains why there is so few examples of locally compact quantum group. I'm not yet with the non-formal Drinfeld twist. So, of course, this thing generalize groups. Sorry, trying to. No. Yeah, okay. So that means a given locally compact group, I will always assume my group to be also second countable. You can build up two locally compact group in distance. So either you start with the function algebra of essentially bounded, so function on the group, the coproduct, which is just comes from the multiplication on your group, and the weights are just the Lebesgue integral with respect to the left or right invariant measure. You can take the group Feynman algebra, so the group the Feynman algebra generated by left translation on L2 of G, and with this co-commutative coproduct. And in this case, left and right invariant weights are the same. There is just one, it's bi-invariant, and just the evaluation at the neutral element, but you have to put it with a bit more care in the general case. So you have to write it this way. Okay. And one very important ingredient in this setting is the so-called multiplicative unitary. So it's a solution of the pentagonal equation. So it's a unitary of two copies on the Hilbert space on which your Feynman algebra acts. And why it's fundamental? Because first you can recover all the data from it. So the algebra and the coproduct. And you can build another one, so the so-called Pontryagin dual, because it generalizes classical Pontryagin duality in the case of a abelian group. And of course, the two examples I gave you are, in this sense, Pontryagin dual, one of the other. Okay, so as I said, compact or discrete is very simple. From analysis perspective, because of existence, you can prove that R weights exist. You can construct it, and non-compact, it's very difficult to construct such weights. So up to now, there is a few isolated example of locally compact quantum group, mostly that comes from the Voronovich school. And three methods of construction. So I will review first these three methods of construction because one of the third will be the one associated with non-formal Drinfeld twist. And the first two, I mean, the first of the first two will pop up by a kind of magic. So let me give you some word about this. Okay, so the first two method of construction is about double crossed product and bi-crossed products, or even co-cycle. There is a C missing bi-crossed product. So the idea is to start with two locally compact quantum group, which can also be a classical group, and to define other locally compact group from what is called a matching. So it's normal homomorphism from the tensor product of the two Feynman algebra of the two quantum groups that satisfies these compatibility relations. If you apply this for groups, I mean, double crossed product, it just you build another group from two groups. So you do not escape from the category of groups. Back-crossed products of group are everywhere because, in fact, for groups, this notion of matching is equivalent to a very, very simple data of a match pair of subgroup. So, and in the most general case, which is what is really interesting here, you just ask. So you have a group, an ambient group. You have two closed subgroups, J1, G2. You ask that they intersect trivially, and that the product of this group covers almost all the group. So the elements on the group that cannot be written as a product of two elements on the different subgroup is of zero hard measure. So that's the only construction. Shan-Majin use this method, but in a less general to produce locally compact quantum group. I think he was one of the first, but in less general situation where you ask that the product is of G1, G2 is G. Okay, we need only to work up to zero measure sets. Okay, and this data, in fact, give rise to measurable action, not by homomorphism, that's the point, of one group on the other, but seen as a set or space, and vice versa. All right. And okay, and so the bi-crossed product, you usually denote it like that. The algebra is just the fundamental cross product of one group on an infinity of the other group by one of these action. And the dual quantum group, you just flip the two copies. But what is very important here is that the multiplicative unitary of a bi-crossed product is just a transformation. So it's a map. So this is a Jacobian, square root of Jacobian, if you wish. In fact, Radon-Nikodym derivative, square root. It's just an operator by composition, by a transformation from G cross G to G cross G that satisfies this reversed pentagonal equation, and this is called a pentagonal transform. And what is very, very nice is that there is a beautiful theorem. I mean, so these things are everywhere. You take any, I don't know, semi-simple Wiley group, you take Iwasawa decomposition, you have a matched pair. You can take GL2 of R or of C or GL2 of any fields. It's a matched pair of two AX plus B groups. So they are really everywhere. But not only they are everywhere, even if they try to hide themselves, you can recognize them immediately because of this theorem by Baj and Skandalis, which says that in fact, every pentagonal transformation, so there is two more assumptions, but okay, comes from a matched pair of locally compact groups. So as far as you find a multiplicative unitary which is of this form, so composition by a pentagonal transformation, then you know that you are in presence of a bi-crossed product. So it, yes?
The Delta data.
Sorry, the what?
The new co-product up there, do you just...
Yeah, I don't want to describe it.
But you've just modified it.
Yes, I mean, it's a non-trivial modification that use the coproduct of an infinity of G2, the coproduct of W star of G1, and everything is kind of transformed by this measurable action alpha beta. I don't want to describe what is the message is that those quantum group you can see just from this the point of view of multiplicative unitary, and they are pretty simple and everywhere. That's the message. All right. And plus something very important. So this is about co-cycle by Coset product. So as far as you have a multiplicative, a pentagonal transform, you can plug in front a function which takes value in a complex number of modulus 1, and you can restrict yourself to function for which this new unitary still satisfies the pentagonal equation. And if you look at the group of function from X cross X, so X is the space on which your pentagonal transform, so your measure space, okay, X should be a standard measure space. I will not give many details. So you take the group of functions such that this new unitary, which is, so I identify function and operator of multiplication by this function, is still multiplicative. And I mod out, if you mod out this group by trivial, so this is called pentagonal cocycles, the element of this group. And this is trivial or Kobanaway's pentagonal cocycles. If you divide by this, then you obtain some very nice cohomological group, which is called the pentagonal cohomology in degree 2, or the match pair cohomology, or the bi-Coset product cohomology. And so this is a difficult question to identify, classify this cohomological data, but each class corresponds a new quantum group in the sense that it will not be isomorphic to the quantum group, to the bi-Coset product. So this is a very important thing. And in our construction, in fact, we will build many classes of this thing. Okay, and it's in fact behind there is a real cohomology theory, I mean differential complex, which is called the measurable CATS complex. So this is the cohomology of this in degree 2 of this complex. So it's really, but in degree 2, it's really easy to describe by this one-line thing. The differential complex is very hard, I think. All right. Okay, so that's what about double Coset product. So just double Coset product. What I could have said is that double Coset product contains, as a particular example, the so-called Drinfeld double. Okay, Drinfeld double is a way to, starting with a quantum group, to associate it the dual of this quantum group to build something bigger, and this is contained in double. But double for group is just group. And bi-Coset product comes with this cohomology pentagonal or cohomology or CATS cohomology, which is very important. Now comes from the third method, generic method of construction. So this, in fact, this boils down to the first ideas of Drinfeld in the years in the 60s, I think, about how to construct what is a quantum group, how to construct quantum group. So this equation here, if you permute this omega with the letter F, you have the equation of a Drinfeld twist. Okay, so we are in operator algebra. So my Drinfeld twist will not be an element of power series with coefficient in the universal enveloping algebra of a given Lie algebra. No, it's directly an operator unitary that lives on two copies of the phenomenon algebra that define your quantum group. So if you start, okay, and that solves this equation. So just a word, if you start with a group seen in this way, you are just dealing with ordinary two co-cycles, so classical group cohomology, measurable group cohomology. If you start with the same group, but you look at it from the dual side, you obtain what is called a non-formal Drinfeld twist, okay? Because the convolution algebra is the analytical replacement for the algebra of power series with coefficient in the enveloping algebra of a given Lie group. So that's the correct setting. Okay, but what is and this equation is just to guarantee that if you conjugate your ordinary coproduct with this omega, then you keep co-associativity. But so that was from the early day. That was the motivation, formal, non-formal. I mean, that's the same idea. But in the non-formal situation, so the problem is the R weight. So of course, the notion of R weights is a notion of invariance, which is associated to the coproduct you start with. So if you deform the coproduct, you deform the notion of invariance. So you have no guarantee at all at the beginning that if you solve this equation, that you will have invariant weight. And that's what Kenny de Comer proved in the years 2010, which is really a great job. In fact, he had to come to a more general situation, which is about Galois object for locally compact quantum group. I will say a word in a second, but now we have a theorem that guarantee that if you can solve, you find a group and you can solve this equation for a group, I mean, find non-trivial solutions, then you build locally compact quantum group. And that's exactly what we are doing. Okay, just last line saying that this deformation procedure basically do not preserve nothing. Okay, not even the compactness. Okay, so what is our goal? In fact, we are halfway between goal and dream. It's to quantize, to construct such a non-formal Drinfeld twist for all Frobenius Lie groups, real Lie groups. So what is a Frobenius Lie groups? I mean, let's say strongly Frobenius. It's a Lie group, a real Lie group that possesses an open dense coadjoint orbit. So we need to add this dense, what people call the algebraically Frobenius algebra of Frobenius group is just open coadjoint orbit. We need more. We need open dense. And we think that we can solve that question. At least I will present some partial answers. So about the examples of Frobenius Lie group, in fact, you have the so-called seaweed, so that's biparabolic subgroup of GLN or SLN, so that matrix group, and you just take intersection, so you take one first parabolic subgroup, and you take another one, don't need to be symmetric, and you take just the intersection. So that's seaweeds. And seaweeds, there is a lot of, in theory, a lot of open questions. So people are still working with this thing. And the basic example is the affine group, the full affine group. And in fact, so of the n-dimensional real vector space. But in fact, we can work with any, so we can, so we have solved, I will give you the class of Frobenius group for which the question is already solved. In fact, we understood, because our construction does not rely on Lie theory at all, that we can extend, in the case of an arbitrary local field, so non-discrete, locally compact topological field, being Archimedean or not, being commutative or not, any field. Yeah. No, there is condition. There is there is a bit more condition. But yeah, it's an intersection of some type of two parabolic subgroup of GLN R. And you have to think at matrix algebra that are these forms, kind of. Okay. So, and the main tool is nothing than, so the guy is right behind you with Nash, sitting in front of Nash, is the Cohn-Nirenberg quantization. So in fact, everything boiled down to projective representation theory and a tricky way to construct, in general, a quantization map. All right, so here is our first important theorem. And this theorem that is our guide. It doesn't solve nothing because it doesn't say when it doesn't produce example, but it's our guide. So take a group G and take a representation that you assume to be square integrable, irreducible, of course, and projective. So projective representation is almost a representation. So P of G1 group element pi of G2 is not pi of G1, G2, but it's pi of G1, G2 up to a phase that depends only on G1 and G2. And this phase, omega, is in fact a two cocycle in group cohomology. So that's what we need. And so under two assumptions that the twisted group phenomenon algebra, so this is, if you wish, the weak closure of the algebra of L1 function with twisted convolution product. So you write down the formula for convolution product, and you add the two cocycle omega pi associated to this omega middle of your integral, and you have what it is, this thing, and the condition, so it's very rigid. We need that to be a type 1 factor, isomorphic to B of H. Second condition, you need, so if you take the tensor product of pi and its contragradient, okay, this the dual representation, it's no longer irreducible, that's for sure. And the second condition is that is unitarily equivalent to the regular representation. And in this case, we have a dual two cocycle. So if H1 and H2 are satisfied, we can build up the guy. Okay, that's our important theoretic theorem. It gives no solution of which group has this property, but that's the guide. I will not explain the ingredient, just saying that here is the Galois map. Is a Galois map that pops up in a very natural way. So let me just skip the next slide. Yeah, so it's okay. Just 1 second. So this, okay. Yeah, two things. This op is precisely the unitary equivalence between these two representations, so the pi times pi c and lambda. So I call this unitary op. You'll see why in a minute. Sorry. And just to tell you that representation theory pops immediately in this party. In particular, there is a very important role which is played by the Duflo-Moore operator, or formal dimension operator, that is related to the square integrability property of the representation by this formula. And this operator is an injective, unbounded operator that here. So that's in the analysis part that I will not explain, it is really important. Okay, and that's the rest of the explication, what were the notation, but just retain that if we have these two assumptions, so twisted group phenomenon algebra type 1 factor, and existence of unitary equivalence between pi times pi c and the left regular representation, then we have what we want. Okay. So now we'll make two interludes. First about, I don't know what, first about the second assumption of unitary equivalence. So why I call this unitary operator, so it's a unitary operator between L2 function, which is the representation space of the left regular representation, and the tensor product of the Hilbert space on which the group acts via this projective representation pi times its opposite times h bar. So what do we call this quantization? Because in fact pi times pi c is the same thing than so the Hilbert space h times h bar is the same thing that the Hilbert space of Hilbert-Schmidt operators on H. So at the end of the day, my unitary equivalence O is a map, unitary map, linear map from L2 of G to Hilbert-Schmidt operator on the Hilbert space representation. And it's why I call it a quantization map. And now the question is, okay, but how can you construct a quantization map, or how can you, where does it come from? In an equivariant way, that's the point, of course. And the point is that, okay, this could be a theorem if I would have put it a lot of assumption, but I just want to take it like, again, another guide. And my claim is that, in fact, if your representation is on some homogeneous space, is acting on some homogeneous space for your group, then such a map is uniquely characterized by a single radon measure T on the product space. So Q is this homogeneous space on which, on L2 function of which the group projectively acts. And the point is that all the classics, all the classical quantization are this form. I mean, it's just my, I can produce the T from the up, so I can look at what happens for the Weil quantization, the Condier-Humbert quantization, the Wieg quantization, for instance, which are seen as I mean, where the behind the group is just the abelian group R2n, but you use the Schrödinger representation that you view, so of a non-abelian group, the Heisenberg group, but that you can view as a projective representation of R2n. And so just to, what is this radon measure? So for Weil, it's just the integration of the anti-diagonal, which is funny. If you do integration on the diagonal, you get nowhere. Condier-Humbert, the one I will be interested in, just you plug the Dirac mass at 0 in the first variable and the Lebesgue integral in the second variable. So it's kind of opposite thing you do in both variables. And the Wieg is just integration against the Gaussian measure, basically. Okay, and I will not tell you why, because for the time being, just, I mean, I can only work with this type of quantization, but just imagine if you are not an Rn or R2n, you can just, if you are in a group, abstract group, general group, you have an immediate analog of this measure, which is just Dirac mass at the neutral element of your group and integration with respect to the R measure. So there is this quantization just, or the radon measure behind the Condier-Humbert quantization generalize really, really easily. Okay, and now another little couple of remarks concerning the first assumption in our theorem that the twisted group phenomenon algebra should be a type 1 factor. In fact, so if you call H1 H capital I2 of G T, the class of the cohomology class on degree 2 on the group which are such that the twisted group for normal algebra is a type 1 factor. In fact, this set, because it's no longer, it's not a subgroup, this set is isomorphic to the set of equivalence classes of Galois object, of G Galois object for the group, which are also type 1 factors. So just to say that, so what we really need to, so it's why this thing is important, and what we need for the first assumption is to understand, to classify those cohomology classes. Okay, and the rest I will just skip. Okay, so now I will present, so yeah, 25 minutes. I will present three classes of example where we have pretty well understood what is going on. Okay, so the first class of example is a class of semi-direct products that satisfy the something that we call the dual orbit condition. I will explain you. So you take with you start with an abelian locally compact group, and H, a subgroup of the continuous automorphism group of your abelian, and you form the semi-direct product, okay? And so you say that this semi-direct product satisfies the dual orbit condition of depth 1. If you can find, in fact, I will rephrase it, if there is, so the group H acting on V acts also on V hat, the Pontryagin dual. That's the dual action. It's just, I mean, it's always there. And so you look at the orbit structure for the dual action of your dual group V hat. And what you ask is that you have an orbit of full measure. This is equivalent to what I have written, on which the group acts simply transitively. So that's the dual orbit condition of depth 1. And more generally, you say that it satisfies dual orbit condition of depth L. So you just drop the fact that the stabilizer of the orbit is trivial. You just ask to have an orbit of full measure, and you ask that the stabilizer of this orbit is of the same form and satisfy this condition at order L-1. So it's an inductive definition. So for instance, GLN of K any field, semi-direct product with K to the N, so K any field satisfies the condition with L equal N, exactly. Okay, so yeah, Mackey classified the representation, all the representation theory of semi-direct product are completely classified by Mackey. This is the Mackey machine construction, and they correspond to pairs, which is one orbit or one point on the orbit, and a representation of the stabilizer. But because our stabilizer are the same form, the representation theory is completely described by the dual orbit structure step by step. So for step 1, you just have a very simple induced representation. The only I'm first looking for or looking at ordinary representation. For depth 1, you have this more complicated thing, and just you have some red here. So this e to the I bracket psi v, it's just a stupid notation to indicate the duality pairing between V and this Pontryagin dual V hat. So we don't have a will-valued pairing in general, even though in most of the case there is, but it's just because we want to use additive notation both on V and V hat, which is a bit crazy because V hat is a group of homomorphism from V to the complex number of modulus 1. So the natural notation will be multiplicative, but we don't want this. We want additive notation. It's why this I to the thing, it's just the duality pairing between V and V hat. Okay, one condition, so condition H1 is satisfied in that situation. Very easy to prove. Very, very easy to prove by induction. And this pi is unique, so genuine representation. So this means that for all these groups, the trivial class is already non-trivial. The trivial class in group cohomology of degree 2 already produce a non-trivial result. And now, okay, so in order to determine the two co-cycle I can build, okay, I make two more assumptions, but that's technical. So, well, the basic thing we ask is that in this group H, so the group that acts on V, so you have a subgroup which is a stabilizer of the dual action that I call J prime, but yeah, what we need is that there is another group, subgroup, closed subgroup Q, such that this pair of subgroup form a match pair for H. So at the end, the structure of the group for depth 2 is what? So you have this H that acts on V, and this H is, say, the double crossed product of some guy Q times some guy that satisfies the dual orbit condition of depth 1. And for depth 3, just to see how the thing is going to grow depth after depth. All right. Then just to tell you that, so this is our very important theorem. So for this, for the time being, we are constrained by, I mean, we can only prove what we need for depth 1, 2, 3, because then we lose some control of some thing, but I'm pretty sure the theorem is the same. Is that so? If you work out the Nuremberg quantization, in a very natural way, so one part is Dirac at some element of the group, the other part is integration. Okay, you have to add a density, but whatever. But then the conclusion of the theorem is that we have an unitary quantization. So unitary quantization plus the knowledge that the group von Neumann algebra, there is no co-cycle because its representation is a type 1 factor, solve completely the problem. And for L equal 1, the two co-cycle we built are very simple, very, very simple. For L equal 2, it starts to be a bit more complicated. For L equal 3, it's clearly not nice, but we have the formula. And what is very important, I could have started with this, is that in the simplest case, so the case of the fine group of the wheels, our construction reproduce the correct analytic version of what is called the Jordanen twist, which is at the base, which is on which kappa deformations are based. And this correct, so kappa deformation in the formal language, so you have E and H, which are the Lie algebra generator of the AX plus B group. So H is the dilation generator, E the translation generator. So the table is H bracket E is E, okay? So in guys working with formal Drinfeld twist, so they exactly have this formula, but without the absolute value here. and without the I here, and plus a little parameter H bar. And they found by hand that this thing satisfied the Drinfeld-Tweed relation. And many years after, so kappa deformation is in fact comes from Jacinto and collaborator independently by Oleg Oliegowski. And yeah, some later, Stachura, so a Polish colleague, that was trying to use groupoids method to produce locally compact quantum group, found what is the correct analytic version. And so this formula belongs to him. Okay, and you have a non-trivial, in fact, he realized, which is also what we realized, that you have to go to the non-connected IX plus B group. You cannot work with the connected part. And of course, then if you want to write an operator just with the Lie algebra generator, you need to explain how to pass from one connected component to the other. And this move is taking care of the things is taken care by this part of the operator, where here CH is the duality pairing, in fact, of the self-dual abelian group Z over 2Z. This is Z over 2Z. And this F is just this element. So you just reverse the sign. And what is really funny, so this formula by Stachura is already very nice, but what is very funny is we exactly fall down on it. But it's just funny. In fact, it's not serious. There were no choice. I mean, one guy did a very complete example with AX plus B, we too, but in fact, there is only one, so it has to be the same. I mean, it could have been in the same class, but it's exactly the same. Yeah.
This group, you know that L1 and not something higher.
Yeah, because if you look at the dual orbit condition, so it just R star that act on R dual, but it's just acting by opposite way, and there is one single orbit which is R star inside R, so it's immediate. Okay, I can write the thing for you later on if you wish, but it's really immediate. Okay, second example, that's also very, very nice, I think, because now we really need to use a projective representation. And in fact, reading a paper about quantum group, finite dimensional quantum group by Ettingoff and Gelacki, I realized, sorry. I realized that so in their paper, they have a formula for a twist, but for a finite group. And I realized that if I change my integral in sum, and I change my measure to the counting measure, we have the same formula. So we say, oh, come on. Guys in finite group have the same formula. So it should be a path to put everything in the same basket. And in fact, this path, so we got the idea from a student of Gelacki and Ettingoff, puts in the same basket every quantum group non-formal based on Drinfeld-Twist, which was known up to now. I mean, except the depth 2. So let me explain you quickly the construction. So again, you take two groups, Q and V. V abelian. Yeah, why V? Because in most of time it's a finite dimensional vector space, so V vector space over a local field. Or you take homomorphism, continuous homomorphism from Q to the automorphism group of V. And you are going to not taking the stupid semi-direct product, but you are going to consider an extension of V by Q. So this means that Q is no longer a subgroup of G. And such extensions are in fact classified by cohomology of Q with value in V in degree 2. So you take a 2 cocycle of this form, so a measurable map of this form. You form the extension. Okay, you can realize this group as a Cartesian product, but with this group law. And that's going the group you are going. That's the groups we are going to quantize, and where everything fall down. So okay, and the only extra ingredient is to take one cocycle, continuous, but it's automatic here, on Q with value on the dual. So one cocycle is just a measurable map. Oh, sorry, here continuous map that satisfies this rule. This we can, yeah. And we make two assumptions. The first one is that it's essentially bijective. That is, as a map, it defines a measure class isomorphism, which is in fact equivalent to this pair of group to be a match pair for the dual semi-direct product, and that this one cocycle is compatible with the extension class, meaning that the cup product of this one cocycle and this three cocycle, which value in a dual abelian group, so the resulting class, cup product class, is a three cocycle with value in the complex number of modulus 1, and the assumption is that this class is trivial. Obviously automatic if you are working with a semi-direct product, if your extension class is trivial, or if your one cocycle is trivial. And now, so what are the examples? In fact, and that's what I prefer the most, the commutative G hat times G, V hat times V, that contains, so that was studied long ago by Irvin Segal, André Weil, that will reproduce the Weil twist or Moyal twist. What do? You just take Q is V hat, no action, and you take for the one cocycle just the identity from V hat to V hat. And this is non-trivial in this case because when you have no action, one cocycles is the same than one cohomology. It just there is no co-boundaries. When there is no actions, there is no co-boundaries. Then we will recover all the finite group examples, so by Ettinghoff, Jelaki, and their students. So that's some examples of the group they can manipulate. And in this case, essentially bijective is just bijective. And in this case, the one cocycle cannot be trivial, has to be non-trivial to be. I mean, it's necessary to be non-trivial to get something bijective. We get also in this single setting the dual orbit condition of depth 1. So that corresponds exactly to the case where the one cocycle is trivial. It also covers another example that a PhD student of mine deal with some years ago, which is the situation where V is discrete and Q is compact. So which arise in a p-adic setting. And here the one cocycle also is non-trivial. And I was very glad to put also this example in the same setting. It has many generalization. And last but not least, it also covers examples where V compact and Q discrete. So we have basically all the possible topological cases. And so in fact, we can build such So group V, group Q, one co-cycle, two co-cycle, eta, beta, from any set theoretical solution of the Yang-Baxter equation. So it's the same. So a bit more generally from any Brave structure. So if you have a Brave structure on a discrete group, finite or infinite, that's just the little generalization from the set theoretical solution of the Yang-Baxter, you can build all what you need. And this is contained in our example. Okay, and then at the technical side is how to construct the projective representation, but I will skip this part. Okay, so, but just the message is that at this point you have to sit down and to really construct the representation. The quantization, we know what it should be. Where am I? Yes, sorry. Yes. Okay. No, sorry, I'm going the other way around. What do I do? I'm lost in my files. It's not at all where I was supposed to land. Yeah, okay. Yeah, okay, okay. Okay, so, and the theorem, important theorem, so for all these things with essentially bijective one co-cycle, so that covers all these type of examples, the multiplicative unitary is indeed a pentagonal transformation. And it's a pentagonal transformation, which, I mean, it's a co-cycle pentagonal transformation. So we have a pentagonal co-cycle, theta, and a pentagonal transform. And this pentagonal transform is fixed. I mean, it doesn't depend, it only depends on the choice of the one co-cycle, but it's fixed in the sense is that it doesn't see the different groups we are quantizing. Only the pentagonal co-cycle sees it. Okay, and the pentagonal co-cycle is, okay, we have an explicit formula, but again, it's why I started to say it's very difficult to construct pentagonal co-cycle indeed. Have you seen, we could not have found, nobody could have found this formula by accident. So we have just followed our construction and then it pops up. All right. Okay, so the conclusion is that with this bijective one co-cycle thing, the locally compact quantum group that we construct is in fact a co-cycle bicrocycle product for the dual semi-direct product, so Q acting on V hat, but with a presence of non-trivial pentagonal two co-cycle. Okay, the rest I will just skip if you permit. And the last thing I will say is that in the case of GL2 cross R2, so this is an example of depth 2. So we already have an omega dual two co-cycle that correspond to the unique representation of this group. But there is a non-trivial, another non-trivial class in this set of cohomology classes, which is associated with the metaplectic, well, say, to a lift of the metaplectic representation. So the metaplectic representation, it's a projective representation of SL2R, or say differently, is a representation of a double covering of SL2R. And this metaplectic representation, you can lift it from SL2 to GL2, and then trivially to GL2 cross R2. And we get the second and last class in this cohomology setting. And I mean, this is really recent. So and we are able to write down what is the associated projective representation. It starts to be crazy, but I mean, it's a fact of life. The only thing we don't know yet is if the Kohl-Nirenberg associated Kohl-Nirenberg quantization is unitary or not. And the only problem is because of this. In fact, we had to choose a very specific representative of the standard metaplectic class, which has some nicer properties. But this nicer property for some part of the questions are nasty for the question of unitarity. So for the time being, we cannot play with the two on the two sides, but at least yes. So we don't have the second yet two co-cycle that correspond to this metaplectic class, but we know that it's there. Couple of weeks, months, years, maybe we'll have it. Okay, so I just stop now. Thank you.
From the audience or online? Really?
Sure, sure.
So these Frobenius groups, are they all solvable?
No, I mean, they are not all solvable. They are solvable in just in dimension one. I mean, there is non-trivial Levy factor. There is no, that's not what I wanted to say. If you take GL2 cross R2, you have SL2 inside the subgroup. Do I say okay, perhaps I'm wrong. Sorry. Okay. Give me a bit more time. I will. I need to think a little more. Okay. Thank you. Yeah.
Back on page 17, you said you had to go to the whole real line, this dilation.
Yes. Yes.
And it's the log of the translation, 1 plus I. If you work on the half line, log of minus ddx squared.
Well, if you work on the half line here, if you work on the half line, of course you can give meaning to this part. But because you have introduced this absolute value and you cannot do otherwise, if you want to have a unitary operator, the two co-cycle equation is destroyed.
What I was wondering is from the half line, log minus ddx squared is canonically conjugate to the generator of dilations. So
yes,
their commutator is pi or whatever.
Yeah.
There's no way to force the phase in at that point, or because you've lost the sign, you don't have anything to work with. Is that the point?
I don't know. What I can tell you is that we believe that so if you just take the positive part here, there is no unitary dual to co-cycle. There is co-isometric, but no simultaneous isometric and co-isometric. So perhaps there is what people call now partial quantum group behind, but certainly not quantum groups.
Audience or online?
Kind of very briefly at the beginning of this, with monoid algebras instead of secret algebras.
Yes.
So is everything, if you try to do it with secret algebras, is everything just
For dual co-cycle quantization, yes, because this unitary will not be unitary in C star, but they live anyway. But once you have built up your quantum groups, then you have a procedure to go down to C star. And yeah. But it's why for this type of question, fundamental algebraic quantum group is much more adapted. But at the end, you can, if you want, go back or go down to C star, reduced or full. So is the two pictures. So there is three equivalent pictures. Reduce, C star full, and fundamental. And you have a way, basically the multiplicative unitary helps you to go from C star to Van is kind of clear, but to go the other way around, you can do it with the multiplicative unitary.
That makes sense.
With co-cycle, the von Neumann algebra, and you also needed it to be type 1 factor. Does this imply that the group von Neumann algebra or locally compact group, quantum group von Neumann algebra is also type 1, or can it be more complicated? And
No, it can
adding
be,
the
no. Just let me give you an example. No, it can be much more complicated. It must be much more complicated. For instance, in the p-adic situation, so you have this. You take this principal unit group of the multiplicative group and you let it act on the quotient of QP by P minus N. The minus is very important, ZP. So the representation theory by Mikey is given by Mikey, and there is the many finite number of open orbit, and then the group fundamental algebra is a direct sum of a finite number of B of H. It's no longer a factor. But you know, when we so that's first easy statement. Yes. No, sorry. What is the? Yeah. So now, when you deform this Fourier quantum group, you do not change the fundamental algebra. So if you do it for the group fundamental algebra, so the group fundamental algebra is what it is. The assumption of being a type 1 factor is somewhere else, not at the level of the algebra.
No, and that appears not to be the case. So we'll thank Victor again.
Okay. Thank you.